Yes, good morning. My name is Johannes Tlatlik, and I work for the Fraunhofer Institute for Mechanics of Materials, IWM, in Freiburg, Germany. And today I'll be talking to you about cleavage fracture under dynamic loading situations, and more specifically how local crack arrest fundamentally changes and influences the behaved fracture behavior. Okay, to understand and grasp the problem at hand, it's probably best to get back to something called the master curve concept. We see in this picture right here fracture toughness over temperature, and if we apply a quasi-static isothermal load, very standard at very low temperatures in the lower shelf region or in the ductile to brittle transition region, we can see a fracture pattern here which you can describe by statistics. And this is the basis of the master curve concept, which is basically a tool, a probabilistic tool, how you can assess cleavage fracture on a probabilistic basis. And you can see here that the experimental data actually matches the outcome of the master curve concept quite well under quasi-static testing conditions. Now what happens if we apply a dynamic load? We can see here, we all know dynamic forces cause a dynamic embrittlement, and we end up with a lower fracture toughness value experimentally than compared to quasi-static testing conditions. However, if we increase testing temperature, we can still see this characteristic increase in fracture toughness over temperature. So now what's the problem? Well, the problem is if we apply this master curve method, then we can kind of see here that there are experimental values that are much higher than predicted by the master curve concept. That's basically in a nutshell what the problem is. Now the reason for this can be connected to adiabatic heating. So we can all imagine if testing if testing time is reduced, then the dissipated heat in the crack tip region has less time to dissipate in the specimen. And so we have a temperature gradient. And so we have locally an increased value in toughness. So that's why the expected or the experimentally observed values are much higher. But is that the only cause for this discrepancy that's observed? And the answer is no, because recent research has shown that local crack arrest incidences are highly relevant under dynamic loading situations as well. What do I mean by that? Well, if we take a look at an SEM picture right here, this is the cleavage fracture right here, and we have a fatigue crack down here, and then upon load we have a ductile damage going on right here. And in the immediate crack tip region, we can observe on the fracture surface actually these island characteristic shapes, and they're also referred to as cleavage fracture islands. And they're clear evidence that sometime during the load history, we don't know when, cleavage is initiated. We can see that in the facets right here, and they have arrested after several microns, maybe 100 microns of crack propagation. This can range to about, we see these diameters of about 50 to several hundred microns in diameter, but they're relatively local incidences. They don't have to do with macroscopic crack arrest or anything like that. But the point is here that we can imagine that this fundamentally changes the fracture behavior, because cleavage no longer is linked to the weakest link concept, where cleavage automatically leads to global failure of the entire structure, but fracture is actually postponed. Now we can quantify these arrest incidences if we count them per specimen. So one icon here represents one specimen and how many arrest islands we find on one fracture surface. And we plot that over the achieved fracture toughness. We can see here that for a relatively high crack tip loading rate at 3 different testing temperatures, we can see that, first of all, even at very brittle conditions, we have a high relevance, or not high relevance, but at least some relevance of local crack arrest incidences. But as soon as we increase testing temperature, this is usually the case that every single specimen arrests at least twice before it leads to global failure. This can even go up to about 15 times. What's interesting here is too, if we lower the crack tip loading rate, so the dynamic loading goes down, then we would all expect maybe, okay, the arrest becomes less relevant, but that's not the case actually. We see here that at lower crack tip loading rates, we even have the same relevance of local crack arrests here. So that's a very interesting conclusion, that the the fracture behavior is fundamentally changed as soon as we become as soon as we elevate the loading level just a little bit. So the next step would be what happens if we use a local approach model to assess cleavage fracture. So we use a FEM analysis and later on try and use a local approach model to assess fracture behavior. Now the important thing here is to note that it's just a standard simulation. What I did here was explicitly try to consider heat generation and also heat conduction in the crack tip region, as you can see here. So we inherently conceive this effect of the temperature increase in the crack tip region. So later on, if we assess cleavage fracture probability, then the temperature parameter here is already conceived. Not going to get into too much detail about the model because it's a topic on its own, but basically it's a relatively sophisticated model from 2010 from a colleague of mine, and it has an instability term which is governed by the maximum principal stress, similar to the original Berreman model. However, it also considers the probability of defect nucleation, which is governed by plastic strain, and we also have stress triaxiality here, so we have a bit of a local constraint consideration as well. Important in the end, however, is that we still use the weakest link statistics to assess the probability of failure of the entire structure. Okay, so if we calibrate the parameters in the model for quasi-static testing conditions, there's no surprise that the experimental results, which are the squares here, are met quite well by the model. This is fracture probability over the load for various testing temperatures right here. So the question is, what happens if we apply the model to the dynamic loading conditions? And we see something entirely different. For one crack tip loading rate and these same testing temperatures, we can see different things. First of all, for relatively brittle conditions, the model, well, it can describe the experimental data quite well, relatively well. However, if we have an increase in testing temperature, we also have a systematic increase in the model error. So the discrepancy increases. As you can see here, it's quite a big conservatism that originates here. Again, if we consider the low crack tip loading rates, which are the circles right here, 10 to the power of 3 megapascal square root meters per second, then again, even though this isn't really that dynamic, that corresponds to a striker velocity of about 0.025 meters per second, so there's no inertia effects or anything. It's really just a little bit faster than quasi-static. But again, we see this discrepancy. Same thing we saw with the influence of the crack arrest islands. Now the question is, can we correlate this error of assessment, so how good does the solid line match the experimental results, with the observed data on the average crack arrest occurrences? And the answer is yes, we can correlate it. So the higher the error of the assessment of the local model is, the more average crack arrest incidences we actually see on the fracture surface. And remember, we inherently conceive the temperature effects here, so this is clear evidence that somehow the arrest behavior is in there. Okay, so how can we improve our model then? Well, first off, we have to consider how local approach models work. What they do is, in a nutshell, they calculate the probability of cleavage fracture initiation in all the elements of the model, and then they use the weakest link statistics to calculate the probability of failure of the entire structure. And the idea now is that we interfere here with a local crack arrest term. So we determine for every element not only initiation probability, but then also assess is a potential crack that initiates here, will it arrest, yes or no? And if that's the case, if it will arrest, it will not be considered for the calculation of global failure. And if arrest will not occur, it will just be considered as it always has been. And this is a topic of its own as well, but basically what we do is we compare locally crack energy with material resistance. Crack energy can be correlated with the maximum principal strain and the crack length. And material resistance is just a fictitious, we don't know what it is. It's somehow a material parameter which is temperature dependent. Okay? And so if the material resistance is higher at that local point, then the crack arrest, then the crack energy, then arrest will occur. So what happens to our model if we apply that? We have fracture probability over load again. And these are the experimental results. And now we fit the model, which is the solid line, to the experimental results again. And we can see here that it matches, not perfectly, but a lot better, which is this dashed line right here is the original model. And what we have now is we have a clear separation between initiation probability and failure probability, because before it was the same. But so we have initiation probability right here, and what the arrest term does is it kind of visually pushes down the probability of failure, so the probability of failure occurs later. So we have these different distribution functions that we need to correctly describe the experimental data. So this gap between initiation and actual failure is now attributed to the Arrest Criterion. And just to give you a brief overview of what happens now, these are the experimental results for all kinds of dynamic testing conditions. And the solid line is now the modified model with the Arrest Criterion, and the dotted line is what the result is with the original model. And we can say that in all cases, the assessment of fracture probabilities improved, in some cases even significantly. Okay, so last slide, conclusions. The things that I want you guys to take with you is, for one, cleavage fracture under dynamic loading conditions is strongly influenced by local crack arrest. The question is now, why is it not influenced under quasi-static conditions? Well, there's two reasons. Both are linked to temperature. First off, if we have fracture toughness over temperature here, we can see that if we apply dynamic load, or the fracture toughness curve is shifted towards higher temperatures, and once a cleavage crack is initiated, it doesn't care. It only cares about what actual temperature there is now. So because we are shifted towards higher temperatures, the ductile to brittle transition region, then local crack arrest is promoted here. Also, in addition, we have the temperature gradient because of the adiabatic heating processes, which add to that. So we have an overall increased temperature, which increases the crack arrest probability. And last but not least, I just demonstrated that the local approach models, as they are not capable of describing fracture behavior, even if we consider heat generation and heat conduction. But if we apply a suitable local crack arrest criterion, then we can improve what we want to assess. Okay, that's actually the last slide. I want to thank the Federal Ministry for Economic Affairs and Energy of the German government for funding this project. And thank you very much for your attention.